Hello everyone, this is Sami. I'm presenting our paper, Watch Your Step, Learning Node Embeddings via Graph Attention. The task that we're interested in is learning embeddings for graph nodes. This task takes as input a graph, which is vertices and edges connecting these vertices, and the output is a continuous vector space that the nodes live in. Each node in this vector space will get some kind of coordinates, we call them the embedding for the node. The nodes are closed in this vector space if they're neighbors in the input graph, and this vector space should preserve the structure of the graph, as in if you delete the input graph, you should be able to recover it with reasonable accuracy using this vector space. Why are embeddings needed? Because graphs in their original form contain discrete relationships, for example adjacency lists, but most modern machine learning algorithms, they expect continuous inputs. Graph embeddings is one way of converting this discrete information into continuous domains, and then you can plug in this continuous information into other machine learning algorithms, for example, to do edge classification, to do link prediction, or to do node classification. Graph embeddings has been around for about 2 decades. However, we're interested in the new methods that simulate random walks and pass those random walks to skip-gram models. We do a review of these state-of-the-art or modern methods. These modern methods, they take an input graph, they simulate many random walks on this graph. These random walks will generate sequence of node IDs, and these sequences are then passed to word-to-vec algorithm, which will embed every node ID into an embedding space. How does word-to-vec work? Well, when it receives this walk sequence, or a lot of walk sequences, it randomly samples one anchor node along these sequences, then it samples another node that's close to it, we call this the context node, then it brings the embedding of the anchor node slightly towards the context node using a stochastic update. It does so many times until it converges. The motivation of our method, these random walk methods operate in 2 steps. In the first step, they simulate many random walks, producing some sequences. In the second step, they pass those sequences into some NLP embedding algorithm, for example, word-to-vec. And optionally, they can train yet another model on top of this embeddings. Can we join these discrete steps into a single objective? If we do that, it will allow us to learn some parameters that are used for the random walk simulation and also the context sampling. For example, we can learn the random walk length, which is called the maximum window length in word-to-vec, and also we can learn the coin flips that word-to-vec uses when it selects the context node. We refer to this as the context distribution, and we denote it by Q. Why should we automatically learn C, or the maximum window length? It's because every graph prefers its own unique value of C. Facebook prefers to be embedded with C equals to 2, PPI with C equals to 1, and Wikivote prefers large values of C. Overview of our method. We would like to join these 2 discrete steps, the random walk simulation and learning embeddings via word-to-vec. To do so, we start by mathematically analyzing them. We want some analytical formula of how many times some node U is sampled part of the context for node V. So that means U has been visited K steps after node V, and K happens to be smaller than the cone flip of the word-to-vec context sampling. Let's denote this quantity by dVU, and overall we're interested in the matrix that relates every node pair with some quantity like this. Doing deep walk and then word-to-vec embedding is equivalent to doing matrix factorization on this D matrix. And in this work, we want to have an analytical expression for the expected value of D. The expected value of D could be derived both in cases if word-to-vec was used, which basically means deep walk, or if someone used another NLP embedding algorithm, such as GLOVE. You can notice that both of these expressions have a summation over the power series of the transition matrix. Here the transition matrix is T raised to the power K. We always sum from K equals 1 to C. We have some expression that weighs this power of the adjacency matrix, and this expression is different based on the embedding algorithm. Before we talk about our overall algorithm, we just mentioned the optimization objective. We can think about decomposing D or doing matrix factorization on D using something like singular value decomposition, but there are also probabilistic objectives that are possible. In this work, we use a probabilistic objective, and it's written in this form. G of Y is our model, Y is our embedding dictionary. Specifically, we define Y to be the outer product of two matrices, L and R, and minimizing this expression with respect to L and R basically means that we're decomposing the matrix D using this probabilistic objective. So rather than sticking D in as something that we compute using, for example, these formulas, we want to assign coefficients to these t to the power k. Specifically, we set this vector q so that its entries sum to 1 and every entry is positive, and we want to assign qk to the coefficient t to the power k. Our expectation on D is parameterized with and is differentiable with respect to Q, and it looks like this. So it looks very similar to the expressions on top, except that each coefficient is now weighted by Qk. And obviously we can recover the expressions on top by manually fixing Q to some value. So what is Q? In our case, we set Q to be the softmax of little q, and now our expectation on D is parameterized using these little q values. The final objective that we want is this minimization objective. In this minimization objective, we're minimizing the node embeddings, which are L and R, these two matrices. In addition, we're minimizing with respect to Q, which parameterizes our context distribution. You should notice that this Q is not used for inference, it's only used during training. Only L and R are used during inference. And further, this expectation over D does not collapse to a zero matrix because there is a constraint over Q, which is basically saying that the Q is sum to 1. This constraint is achieved by the softmax activation. Now we look at the results from our method. We show that our method drastically improves the state of the art on linked prediction. It also improves on node classification, especially when we compare it to methods that do not learn the context, such as node2vec. We also show that every graph prefers its own Q, and this corresponds to the optimal if we manually tune the value of C in node2vec. So we see here, for example, that C prefers to be 2 for Facebook, and our Q distribution has learned to put most of the weight on the first and some weight on the other entries. PPI puts all its weight for Q on the first entry, and we see that it prefers to have C equals to 1 when we run node2vec, and similarly we see that our Q for Wikivote assigns some kind of uniform or long tail distribution, and in fact in node2vec it also prefers a larger value of C. We also show that even if you sweep C in node2vec, that's not enough, because if you change C, you don't change the context distribution formula. However, in our case, it learns the context distribution formula that suits the graph, and we show that the best performance is shown as a purple solid line in case of node2vec, but in ours, even if we change the C value in our model, basically we always outperform node2vec. The conclusions are: we reformulate graph embeddings from a two-step process into a single objective. The sampling hyperparameters of these two steps define what we call the context distribution. Joining the two steps allows us to learn the context distribution, which we express as an attention model on the power series of the transition matrix. This is a depiction. So DeepWalk, or the older methods, they always assign the same context distribution irrespective of the given graph, but in our case, our method will assign a context distribution that changes per graph. Thank you.